So first of all, thank you so much to the organizers. It's an absolute privilege to be here talking to you today about framing lattices and flow polytopes. So to start off, this is joint work with Cesar Ceballos. We did this while I was a postdoc at TU Graz, and I'm no longer there, and I'm on the job market. Wink, wink, if anyone has any tips. So I'm going to introduce framing lattices in a bit, but I'm going to start out by telling you why you should be interested in this new family of lattices. And then we're going to look at some examples later on. But you might have heard of the Tamari lattice. It's very interesting. But it's been generalized in various ways, including the new Tamari lattices by Perville, Rattel, and Vianot, 2017. And then there's also another family of lattices called the Dick lattices or new Dick lattices. And I don't really have a good attribution to this because they're essentially just principal order ideals in Young's with So that's another way to think about these. But they were nicely unified recently by Ceballos and Chenevier with what they called alt-new Tamari lattices. So this is one direction you can go with Tamari lattices. But here's another one. You can go through to Cambrian lattices, and I mean type A Cambrian lattices at the moment, and by reading, and these were generalized further to epsilon ij Cambrian lattices by Bilod. And so as part of the extended abstract that we submitted, we also gave a kind of a different combinatorial model for getting all of these lattices that we called them cross-Tamari lattices, with the exception of some boundary cases in the epsilon ij Cambrian lattices. But I won't really focus on those today. Instead, keep telling you about different generalizations of Tamari lattices, so you can also generalize to Grassmann Tamari lattices, which was done by Santos, Stump, and Welker. And these extend further to grid Tamari lattices, which also include the type A Cambrian lattices. That was done by McConville. We have more lattices that I'm exhibiting here. We got the weak order. We have also the S-weak order, which generalizes the weak order that we just heard about in the previous talk. And also a weak order on multi-permutations exists. And there's the Boolean lattice. But why am I telling you about all these lattices? This is the punchline of the talk. They are all captured under this big umbrella family, what we're calling framing lattices. And so that's what I'm going to tell you about. And they're closely related to flow polytopes. So there'll be some repetition of some definitions from the previous talk as well. But also there's more. This isn't an exhaustive list. There's also certain tau tilting posets for certain gentle algebras are included in this family. And yeah, every once in a while I keep finding new ones that I want to see if they are in the list or not, but have not yet checked. So it could grow much more still. But we start with a very basic thing, directed graph, vertex set 1 through n, edge multiset E, and we're going to use a convention today that the edges are going to be directed from smaller to larger vertices. And so I'm always going to be directing edges from left to right, and so I'm going to omit the arrows on the edges so that you can actually see what's going on in bigger graphs. But then we have a route, like we did in the previous talk. It's a path from a source to a sink. In general, we don't require that there's exactly one source and one sink, but just for convenience, we do it in this talk. But everything works in general with arbitrary numbers of sources and sinks. Then we have this flow polytope associated to a graph. So here, as was defined in the previous talk, you can also think about it as a convex hull of the indicator vectors of the routes in the graph. So here, if I have one route, x1, there along the edge x1, another route along the edge x2, then the indicator vectors for those are 0, 1, and 1, 0, where all of the flow goes along x1 and none on x2 and all of it on x2 and none on x1. And so then you take the convex hull of those two vectors and you end up getting the space of all flows of size 1 on that graph, and it's a polytope known as the flow polytope. So let's build a little bit bigger graph here. Instead of this baby caterpillar that we had, we now have a little bit longer caterpillar, and we've concatenated two of them to get a longer one. And in general, what that does in flow polytopes is it's the product of the two flow polytopes that you're putting together. And so we get product of two line segments being a square. And we have now 4 routes corresponding to 4 vertices of the square. So this is a little bit of flow polytopes. But we're going to also talk about a framing of a graph, and this is where the name framing lattice will come from. So a framing on a graph is just a linear order or a collection of linear orders on the edges and of incoming and outgoing at every vertex. So here you have them listed as numbers, so 1, 2, 1, 2, 1, 2, 1, 2 on the left from top to bottom. And the right one's exactly the same, with the only difference being that the exiting edges from vertex 2 are now swapped to 2, 1. But this will get very messy if we have all these numbers on these edges, so there's actually a nicer way to do this than just to draw the graphs so that they respect the order from top to bottom. But that you might have to do some twisting, like in the graph on the right. And so this notion of conflicting routes and coherent routes we saw also in the previous talk. So 2 routes conflict if they come into some vertex in one order and then they leave in a different order. So then they conflict, and otherwise they are coherent. And so you can think of it as kind of a non-crossing condition, with this caveat that if you look at the graph on the right there, P and Q, the orange and the blue routes, are coherent, even though there is a crossing in them, but that crossing is not happening at a vertex, so that's fine. So in general, they can cross as much as they want, as long as it's not happening at a vertex. And more generally, it's possible for 2 routes to come in at a vertex and then share a path and then differ again. So in that case, you just look at the portion where they come into the path, compare there to the place where they exit the path. So coherence and conflicting routes can be checked in those cases as well. And then we take a maximal set or collection of pairwise coherent routes, and that's going to be called a maximal clique. So for this graph that we've been looking at, we have 2 maximal cliques. So there's 4 routes, and 3 of them can be put in one maximal clique and another 3 in another maximal clique. And these objects, on these maximal cliques, we're going to put a covering relation, where delta 1 is covered by delta 2, if delta 2 can be obtained from the delta 1 by a counterclockwise rotation of a single route. So that image there is supposed to tell you how the counterclockwise rotation works. You can think of it as, here's my route with the vertex V as my head, and then go like this. And if you can do that in one maximal clique on one route to get another one, then you have a covering relation. Turns out if you take the transitive closure of this cover relation, you get a poset. In this case, the poset is quite small, only 2 elements, but you get a poset. And this poset is what we're calling the framing lattice because of the following theorem. So these posets are lattices, first of all, and they're also known to be semi-distributive, polygonal, and congruence uniform. And moreover, all the polygons that can appear in these are squares, pentagons, and hexagons. So just a couple of reminders on definitions there. Semi-distributivity just means that the meets and joins distribute over each other under certain conditions. And polygonality means that if you take 2 elements in your poset or lattice and they cover their meet, then the interval between their meet and their join is a polygon. There's not extra stuff in there. And congruence uniformity means that you can obtain this lattice by certain day-doubling moves starting from the singleton lattice. And so how to prove this? Well, we utilize a very convenient and nice lemma by Björner, Edelman, and Ziegler that lets you prove the lattice property by checking the cases where 2 elements cover a single element and showing that they have a join. Then that suffices to prove that the entire poset is a lattice under some nice conditions like finiteness, and I think it must have a 0 hat, a bottom element. But then we check cases look at all the ways these big maximal cliques can interact with one another, and the routes can go like spaghetti all over each other, and you try to figure it out. And it's just small enough and a number of cases that we can do it by hand, and only squares, pentagons, and hexagons show up. So at least we can't tell any deeper reason for why that's true at the moment, but only those ones show up. And then you can prove semi-distributivity by another kind of these BEZ-type lemmas, and then also show that it's a HH lattice as defined by Caspard, de Poly-Barbout, and Morvan. And that just means that you should put a certain type of labeling on the edge set on the Hasse diagram, and then it implies congruence uniformity if you have some other conditions with it. But let's not forget about flow polytopes quite yet. So I introduced them because they're so closely connected with these framing lattices. So like we saw in the previous talk, maximal cliques of routes in this framed graphs are top dimensional simplices or facets in a regular unimodular triangulation of the flow polytope. And that was the result by Danilov, Karzanov, and Koshevoy from FPSAC2024. And here are the two framings of the same graph that we looked at, and the corresponding two triangulations that you get. This is a very small case, but hopefully you get the picture that, in general, this framing lattice is the dual graph of this triangulation, or it's the Hasse diagram lives inside of the flow polytope in this way. And so you can also think of this as a lattice on facets of certain regular unimodular triangulations of flow polytopes, if you want. So some examples to share with you all. So we saw this Aruga graph already in a previous talk. We have this caterpillar, and so you can get the weak order if you use the framing that was drawn here. And the bijection's fairly nice, because you can start with the bottom route that takes the bottom edge of each segment, and then read off your permutation 1, 2, 3, and then in that order bump the ith edge upward. So starting with the bottom one, then to get the next route in the maximal clique, you bump up the first edge, then take that route, bump up the second edge, take that route, and bump up the last one, and you get a collection of routes. If you do it in the order of the permutation, you get an associated maximal clique, and vice versa. Or you can see that it's bijective. But this can be extended to a weak order on multi-permutations, which is less common. So you start out with a parameter s, which is going to be a composition, and it's of some integer m, but it has length n. And so for every number 1 through n, we have si copies of that number I, and take all the multi-permutations like that. You also go up the lattice by doing adjacent transpositions that are increasing to go upward. So you have this multi-Aruga graph now, this multi-caterpillar, and you build it just like the caterpillar, but you have si plus 1 edges in the ith segment based on your parameter s. So there's one example. And the lattices get big very quickly. And the bijection works out exactly the same as it did in the regular weak order case. And also, the S weak order, which was the topic of the previous talk, that can be obtained. And now you take the Aruga graph like we did before, but we add whiskers to these caterpillars, and you get these types of graphs. And we saw examples, very much nicer examples than this one in the previous talk. And I also want to point out that the hard work here was done by the team that Eva was a part of: Gonzalez de Leon, Morales, Felipe, Tamayo, Jimenez, and Yip. We just pointed out that, oh, by the way, here's the partial order from the framing flow polytope perspective, while they had it from the S-weak order perspective. Then also Tamari lattices. How do you get these? So you start with a path with a source, and then n vertices in between, and then a sink, and then you add edges si from the source to vertex I and vertex I to the sink t for every I in n, and you get this family of graphs if you increase n, And for the nth Caracol graph with the framing that's drawn there from top to bottom, the lattice that comes out is the n plus first Tamari lattice. And we can play this kind of same game of adding this extra parameter s, this composition, and then define s Tamari lattices. These are the same thing as new Tamari lattices if you happen to know what those are, just using a different parameter to construct them. But again, we just start with construct it in the same way as the Caracol graph for the Tamari lattices, but we just add extra copies of an edge, Si, depending on the composition S. So there's a small example. And I want to give kind of a sense of what these examples look like, and there's some interesting things that can be observed by looking at these. So first of all, if we're gonna fix the graph now to be the one that is the Caracol 3 graph that's drawn there. But now I've drawn the graph there with the reverse framing of what it had in the previous picture. And it turns out if you reverse the framing, you end up taking the dual of the lattice that results. And this is the Tamari lattice, so it's self-dual, even though it's not clear from that picture that's drawn there. But we changed the framing just a little bit, and it has a very big, at least surprising to me, change in the lattice structure. It's no longer even polytopal in a sense. If you look at it, it's more like a polytopal complex if you fill in some of the faces there. And you can keep changing one edge at a time or two at a time, and you get different types of lattices. And the one on the right there is a principal order ideal in Young's lattice, just kind of a dual of it, I guess. And you keep doing it, and you get various different kinds of lattices. And these ones, this family here, when you're changing the framing of the Caracol graphs, they include the type A Cambrian lattices. Like the third one on the bottom, this one is a Cambrian lattice. And of course, this one is as well on the top left. But some things you might notice about these as well is there are a couple of them that look the same, or are duals of one another, but the graphs are slightly different. So this one and this one, if you look at those two, so there you can see that they're dual from the fact that if you reverse the flow in the graph, then that's the same. That also gives you another way to get the dual of the graph, of the framing lattice. So some pictures to look at and come up with structural properties and think about. I enjoy looking at them, but what are some questions that we could ask about these? Can the Hasse diagrams of framing lattices be realized as one skeletons of polytopal complexes instead of, or in a similar manner maybe that the S weak order was? Potentially it's possible to use some similar techniques. Also, which framing lattices have Hasse diagrams that are one skeletons of polytopes? We don't know. A single graph can have multiple framings, and some of them will give you kind of polytopal ones and non-polytopal ones like we saw in the previous slide. And then what about n regularity? There's some cases that we know where this is true, particularly the ones that are related to the tau tilting posets of certain gentle algebras, but end with this conjecture. This conjecture, as in the extended abstract, says that for a fixed graph, all the framing lattices have the same number of linear intervals of length k for every k greater than or equal to 0. So there, as a small example, we have the two graphs are the same again, but just different framings. On the left, we have the framing lattice that results as a pentagon, a Tamari lattice, and on the right, it's a principal order ideal in Young's lattice, but the dual of it. And these ones have the same number of linear intervals of each length. So length 0, they both have 5 vertices. Length 1, they both have 5 edges. That's straightforward. Length 2, then you have 2 linear intervals here, this one here, and this one here on that side. And the one over here is there and there. So and then none of length 3 and for any k greater than 4. And this is known to hold by a nice result by Ceballos and Genevieve on alt-New-Tamari lattices, which is a nice subfamily. So it's natural to wonder that whether it works in general, and computational evidence seems to suggest that it does. And yeah, so it's really interesting, but I also have no idea how to even approach trying this in the bigger generalities. So I find it a very interesting problem. But with my questions over with, maybe it's time for some of yours. So thank you.
Thank you very much for the talk, and there are many questions. So maybe.
So I was just curious, which principal ideals in Young's lattice can you get from framings? Is that known?
Any principal order ideals, yeah. Yeah, it's, if you think of it as inclusion of Young diagrams, then the Young diagram, the top Young diagram, that you just take the principal order ideal, and there's a way to associate a graph to that top Young diagram, and from that, with the right framing, you get the whole thing. Yeah. Yeah.
Thanks for the very cool talk. I'm curious if you've started to look at like topological types of questions. Like, can you record, say, the number of chains of length k in this in terms of some data about what sorts of flows exist? Like, is there kind of?
It's a very interesting question, but I haven't had time to think about that. But there could be some interesting stuff there for sure. But unfortunately, I don't have anything deep to say about that.
Could you please go back to the previous example?
Yeah.
I just did not understand your conjecture.
Yeah.
So isn't there one interval of length 3 on the left and 2 on the right? I don't understand what you mean.
So.
So, yeah, could you clarify that?
Can you say the question one more time?
So, the way I was thinking was that there's an interval of length 3 on the left, and there are 2 intervals of length 3 on the right.
Right. But they're not linear intervals because as soon as you have the top element of a polygon and the bottom element of a polygon, the interval has to include both routes to it.
So linear intervals just means intervals which are aligned.
Yeah, exactly.
Okay. Thank you.
Yes.
Okay, I think you hear me. Yeah. Okay. So you have a whole family of posets when you fix a graph and vary the framing. Did you notice any how to say it? So any refinement structure when you changed the framing? Like because I know it is true in the special example of the alt-New-Tamari that if you change slightly the framing, you will have a refined or a coarsened poset. And have you looked at it in the general case?
What do you mean by refined or coarsening of the poset?
That means there is a bijection on objects such that it is increasing. So that in one way, I mean, or telling it otherwise, you can obtain the second poset. The second is a refinement of the first if you can obtain it by adding relations to the first.
I don't think you can, at least if the conjecture holds, which it seems to, you can't add relations without adding extra edges.
Like for instance here, if you just, so you've got 5 elements and one is a refinement of the other. So the one on the right, there is more relations. So there is the same number of cover relations. Like for instance, if you just take the, which one is it? The one, you add the relation of the one on the right to the second on the left, then you've got this poset on the right.
Yeah, we haven't thought about that, so the answer is no, unfortunately, yeah. But I'd love to discuss some more with you later.
Oh, I would also like to ask a question, if I may.
Absolutely.
Does this include the shoot-move posets?
In very small cases, or in some cases,
So
yes.
actually, my question is, can you exclude that it includes all shoot-move lattices? Do you have an example of a shoot-move lattice or poset which is not included?
I'm not entirely sure, but yes, we have thought about kind of trying to extend this towards your lattice conjecture as well, and it's the main difference here is that we're dealing with triangulations of a polytope instead of multi-triangulation, so there's still a big gap that needs to be filled, but yeah, we have looked at the connections to the shoot moves still.
Okay, one last question.
Okay, so can you go back to the previous slide?
Yeah.
The example that you showed. Okay, so the third one and the eighth one are the same, but let's say, I mean, the lattices are different. So, like, I mean, like, is that just a coincidence, or are there the reason behind it?
You're talking about the third one here,
Yes,
and the last
and then
one.
the last one, yes.
Yeah, that's a great observation. So there's another operation that you can do on the graph that preserves the lattice, and it's to not only flip it vertically about an axis, but also, or I guess it's a full 180-degree rotation of the graph. So if you look at this one and this is really a full 180-degree rotation of this graph. And when you do that, you're reversing the flow and you're reversing the framing. And so you're taking the dual twice to get back the original lattice.
I mean, like, it's not. Like, I mean, if you actually rotate 180 degree, like the length one things, they're still in the bottom. So I don't think they're really 180 degree rotation.
If you draw them like a little more bubbly, then it should be the same. Yeah.
I would like... excuse me. I would like to propose to move further questions to after the talks. And let's thank our speaker again.